Hello, welcome to this installment of AV Physics 1, Kinematics 106. In this topic, we are going to focus specifically on velocity, a particular type of velocity, constant velocity. Now, if we recall, kinematics is a subfield that focuses on the motion of points and bodies and systems of bodies. We begin by describing geometry and declaring initial conditions of the known values of position, velocity, and acceleration so that we can predict future values. And again, we are looking at an overview of motion. Ultimately, the fundamental quantities that we can measure are position and time. And by measuring position and time, we can determine whether the velocity is constant or the velocity is changing. And that, of course, can then inform what's going on with acceleration. But it all begins with position. We are, in this lesson, going to focus on constant velocity. That's our focus for today. And in a linear environment. So the concepts and formulas and definitions we have, today we will be focusing on this formula and this formula only. And we see it's an average velocity. So let's first begin with some definitions. Speed is the rate the distance is covered. And that has magnitude, which is a number, like 6 meters per second. Velocity is defined as the rate of change of position. That's its definition, the rate of change of position. It has magnitude and direction. So we say it is 6 meters per second north. 6 meters per second is a speed, and 6 meters per second north is a velocity. So some people say that velocity is speed plus direction. Now, again, in kinematics, we can only model one dimension at a time. So we are going to focus on one-dimensional motion along a line. Now, of course, these will look very similar from the position time that we have. But now we want to use the same examples we had in our position time, but analyze them for velocity. So in the example we had in position time, we had starting out with a initial position of 2, and we ended up at 6. It's our instantaneous position, and we traveled that direction. Well, delta x, in this situation, we ended at 6, we started at 2. And let's suppose this happened over 1 second. Well, then we would have 4 meters per second. And that would be our velocity. In this situation, we started with an initial position equal to -6, and we ended with a final position of 2, -2. So our average velocity, which is the total displacement over the total time, the rate of change of position, we ended at -2 minus a -6 all over 1 second. Let's say it took 1 second for that to happen. And we end up with 4 meters per second. So in both of these situations, we have exactly the same velocity, 4 meters per second. They are traveling in the same direction at the same rate. Our second example that we will look at is we will start here at 6, and we will end up at 2, traveling like so, and we have an x0 and an x. So delta x is x minus x naught. So we have 2 minus 6 over 1 second. We have -4 meters per second. So the velocity here is -4 meters per second. Note that there is a magnitude and there is a direction, negative, headed toward negative values. On this side, we will consider starting here at -2 and ending at -6. And here's our initial position and our final position. So we end up with -6 minus a -2 over 1 And that gives us minus 4 meters per second. So again, we have exactly the same speed. And we have the same velocity, same direction. So these two are headed in this direction, so they have positive velocities. These two are headed in this direction, so they have negative velocities. It doesn't matter where you are located. You can have either a positive or a negative velocity. So here's a positive locations, and we have a positive velocity. Well, here are positive locations, and we have a negative velocity. And the reverse of that, here we have negative positions and a positive velocity, and negative positions and a negative velocity. Down here, we'll start with a position of minus 2, and we'll head to a position of plus 2. So we have our initial position and our final position. And we ended up with 2 minus a minus 2 over, let's say it occurred in 1 second. Well, we end up with 4 meters per second. The arrow is pointing toward positive values. And lastly, let's start here at a position of 2 and end up at minus 2. All over 1 second. So we ended up with minus 2 minus the initial over 1, and we end up with minus 4 meters per second. We have an arrow moving toward negative values. We have a negative velocity. Here we have an arrow moving toward positive values. We have a positive velocity. Here toward negative values, negative velocity. Toward negative values, negative velocity. And here positive values, positive velocity, positive values, positive velocity. Now, one thing you might notice then, since v is delta x over delta t, if the delta x is positive, we know the time will always be positive, then we'll have a positive velocity. And if we have a negative displacement, then we will have a negative velocity. So velocity, the sign of velocity, is the direction of movement. It's the same direction as the direction of displacement. V direction is the same as the delta x direction. Now let's look at constant velocity from the perspective of graphs. Position time graphs. If you recall, in the beginning we said we can measure position, so we will look at position time graphs. So let's have 3 curves here. We'll make this one red, we'll make this one blue, and we'll make this one light green. So first of all, we need to make a graph out of this, the axes. And let's first plot it on our motion diagram, our number line. So we'll start out with the red. And the red, let's see, at time 0 was position 2. And a second later, it was at position 2 again. Oh my gosh, it remained at position 2. Well, the one thing we would notice about this is we would say that the velocity is 0. Constant velocity. Yeah, it stayed 0 the entire time. So one thing that's not obvious is that constant velocity can be 0 velocity. It's the number. And if we look at the blue, that started out at minus 2, and lo and behold, it stayed there the entire time. And for position C, it was at 0 and remained there the entire time. So all of these have velocity equal to 0. Well, let's see what the graph of those looks like. So here's our time, and here is our position. Here's positive, and here's negative. So at time 0, for A, we had a position of 2. and at time 1 a position of 2, and 3, and 4, and 5. So that is what a graph of constant zero velocity is. It shows the position was 2 and remained at 2 the entire time. You may also notice that the slope is 0. Now the slope is delta x over delta t, which has units of meters per second. Well, the velocity, and that's velocity, the velocity is 0, so we would expect a 0 slope. Now we repeat for the blue, and that was at minus 2 times 0, and it remained at minus 2. And again, the velocity is 0. There's no change in position. And lastly, we had a position of 0. And there we have it. Notice, of course, that we have this position of 2, it stayed there. This position of minus 2, it stayed there, and 0 stayed there. I just put the number line on side of it so that we can see that this axis really, this axis over here, the vertical axis, is really just the number line. And the graph itself is a projection of that point onto this graph. Now, we can also say that each one of these is a straight line. Y equals mx plus b. The y-axis of this graph is x. The slope is 0. The x-axis is time, and the y-intercept is 2. So we have an equation of x equals 2. Position does not depend on time. So by the same token, you could then see that this x is 0, and this x would be negative 2. So those are the equations that would describe that motion. When we have constant velocity equal to 0, we would expect horizontal lines on a position time graph. Now let's see what happens when we have constant velocity that is not equal to 0. So we'll start out with our position A. We'll make that one blue. And so at time 0, we're at a position of minus 4. And at time 1, we're at a position of minus 2. And at time 2, we're at a position of 0, and then 2, and then 4, and then 6. So we see that there is this trajectory like so. Now to plot those on our graph, we of course need our axes labeled. Time, x. And so we have a position of minus 4 at time 0. So time 0, 1, 2, 3, 4. And then we have minus 2. And then we have 0. And then 2. And 4, and 6. Now our equation of that line is y equals mx plus b. The y-axis is position x. The slope, the slope is delta y over delta x. Well, the y-axis is x, so that's delta x. And the x-axis is t, so that's delta x over delta t, which is the velocity. The slope is the velocity. Whenever we find slope, we want to use the biggest, most extreme points possible. So we have a final position of 6 minus the initial position, which was minus 4. And that occurred over a period of 5 seconds. So we have 10 over 5, or 2 meters per second. So we have a slope of 2. The x-axis is t, and the y-intercept is minus 4. X equals 2t minus 4. And we want to point out that this is the velocity, and this minus 4 is the initial position, x0. So generically then, we might expect the position equation to look like this. X equals vt plus x0, where the rate of change, the slope, is equal to the velocity. I mentioned the projection before. So that's the number line. We went to 0, 2, 4, 6. And that second dimension is about the time. Let's move on to the second. We have at time 0 a position of 4. So I'll do that here. And then it goes to 2, then it goes to 0, then minus 2, then minus 4, then minus 6. Like so. Graphing those, starting at 4, then 2, then 0, then minus 2, then minus 4, and minus 6. Well, let's see. Our equation, we have a straight line. Y equals mx plus b. The y-axis is x. The slope is minus 2. It's the same speed. It's just moving the opposite direction. So minus 2t plus 4. And again, our generic equation is x equals vt plus x naught. Now, looking at the position time graph, the significance of this intersection is the blue and the red objects are occupying the same position at the same time. So if these were both on the same line, they would collide. They're on two separate lines, well, they wouldn't collide. So they must be there on two separate lines. But this models that motion that we have. So next we have the green. And let's see what we have. We start out with a position of 3. Oh, and after 1 second, we go to 2, then to 1, then to 0, to minus 1, to minus 2. So we would expect the velocity is negative, just as we would expect the red to be negative, because it's moving in the negative direction. And so let's write that equation. Y equals mx plus b. The y-axis is x. The slope now is delta v over delta t, delta x over delta t. And we ended up with minus 2 minus 3 all over 5. So we have minus 5 over 5, which is minus 1. We expected the negative, so now we have minus 1 velocity. All right, so now we have minus 1 t, and the y-intercept, the initial position, was 3. So x equals negative t plus 3. So those are our three equations for these particles. Now plotting it on the graph, we started out with a position of 3, then we went to 2, then we went to 1, then we went to 0, and minus 1, minus 2. So we have a negative slope, and we notice it's not as steep. So takeaway is on an xt graph, slope is velocity. The y-intercept is x0. And those are our takeaways from that graph. Lastly, I want to do a little bit of algebra here. We have this equation. The average velocity is the displacement over the time, and the displacement is x minus x0. So let's do some substitutions here. So v equals x minus x0 all over delta t. Now what I want to do next is rearrange this equation. So we have v delta t equals x minus x0. So what does x equal? We add x0 to both sides, and we're left with x equals v delta t plus x naught. And just to keep I'm just going to switch sides. Now what is delta t? Delta t would be t minus t0. If t0 equals 0, then delta t equals t. So x equals vt plus x0, which is what we saw from the graphs when we looked at the line. And that is in the form of y equals mx plus b, a straight line. Now just a reminder that the meaning of average velocity is it's the constant velocity that would produce the same displacement in the same amount of time. Notice this formula is for the average velocity over this interval of time, where we have the total change in position over the total time. So we could have a particle that moves like this, and we could say this is delta x, and it also corresponds to delta t. Now what we would notice then is if we had this little delta x and little delta t's, they would not be equal to the overall delta x over delta t. In other words, we could calculate little delta x over delta t's for all of these. So we could end up with many discrete little numbers. But we can replace all of that with an object that, let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Same distance in the same amount of time. We can apply it to a larger journey, or we can apply it to little intervals of time. But remember, when we do delta x over delta t, there is some interval of time and we're calculating the average velocity over that interval. And that's going to serve us well when we move into our next topic where the velocity will be changing.